Hello and welcome to our next webinar with the topic Heating, Ventilation and Air Conditioning, HVAC. Yeah, my name is Thorsten Reibel, and I share as always with Jürgen Schilder this webinar. Approximately 1 hour, maybe a bit later, a bit more time we need. But what is the topic today? Heating, ventilation, air conditioning, as already mentioned. So we will talk about heating or room temperature control and cooling in general a bit. We'll give you an overview of the sensors which are working in this topic, and of course we'll talk about the actuators as well as the solutions we have. And Jürgen will especially talk about the fan coil unit, control the fan coil actuators, and has also an example, a practical example, based on ETS project together with a visualization software project. So he will show you something practically, and as always, you will get later on all the files, the presentation, but also the recorded webinar in our feedback email, including the project, the ETS project, and also the visualization example. So everything will be available for you later on. And if you have any questions during the webinar, you can write down in the chat on the lower right side. Any question to us? To us means to the host and presenter. So please send it to us, and then we try to answer during the webinar. If not possible, we will give you a reply at latest during or in the feedback email. One other topic is that we have finally a kind of examination for you, a small examination with 4 questions only. So please answer these questions to complete your webinar as a successful participant. If you cannot do this at the moment after the webinar, you will get a reminder 1 week later approximately, and so then you can do it as well at that time. How to do is written in this confirmation email you have got from our administrator and TP Online, and there's also a link behind where you can do this. But we will send you in 1 week also a reminder. Good. Allow me to switch off the video screen right now to improve the performance of the total solution here with WebEx, and I would like to start now with a real webinar. Heating, ventilation and air conditioning. Yeah, here you see all our products related to this topic, heating, ventilation, air conditioning. You see there are some components behind, mainly sensors like the room temperature controller, but also an air quality sensor is part of our total solution, and different actuators to control directly any valve drives or also any fans. Fan coil units can be controlled via KNX, and some other components, some special devices. Here you see an Electromotor valve drive directly connected to KNX to control any valves behind. Here our room master, which has this fan coil control included, so a kind of fan coil actuator is inside this device. And we don't go to all the products, of course, but we show you some solutions around the products with some more details. You see also presence detector is a possible component for heating, ventilation, air conditioning control. So for example, if you leave the room, you can go to any standby set point to save energy, for example. More products will come. This is a key application for us, HVAC, and so already in this year we will have a new device, very interesting one, but in the next future more will come for sure. So let's go to some typical application examples we implement with our solutions in KNX. So the main application is room temperature control. So inside a room we would like to regulate the room temperature. Can be done via a heating solution or via a cooling solution. What you see here, a typical heating situation in some countries with a radiator, so a warm water-based heating system behind. We have to regulate the temperature by means of a valve or controllable valve. So we have such an thermoelectric valve drive, for example, which is not a KNX device, but we are an electronic output. We come to this later on. We can open or close more or less the valve behind. Done together with a room thermostat, and the room thermostat is the heart of the system regarding controlling. It measures the room temperature compares it with an adjusted set point, and then it will send out a control value to regulate the temperature in the room via the valve. Here you see an additional, let me say, a kind of accessory, a window contact linked to an input of KNX binary input, here in this case a security terminal. So in case of opening the window, you will maybe shut down or close the valve to save energy, so nobody can heat during open windows. Yeah? The same for cooling, of course, possible. Any local push buttons can be integrated in the room thermostat, as you can see here, or a separate one can also influence the situation. For example, you change the set point, or you change the operating mode from comfort mode to go to night mode, again to save energy and to reduce the set point in case of heating at least. Yeah, the same solution only with another hardware, again the room thermostat, but here in other hardware it's a direct KNX controlled motor valve drive. We call it continuous control, we come to this later on. But also here the option to connect the window contact, in this case directly connected to this device, because there are two binary inputs integrated. Same results, so it's room temperature control for heating, but a bit different hardware, at least at the actuator side. Or here, a more comprehensive solution, it's again a motor valve drive, KNX, together with a radiator and a valve drive, a valve behind. A room thermostat is necessary, yeah, but we have here additional sensor, like a air quality sensor. This component is able to measure the CO2 concentration in the room, but also relative humidity, but also the temperature. And depending on, for example, CO2 concentration, we operate a blower actuator to get more fresh air into the room. So we can increase the speed of the fan. Maybe it's natural ventilation, whatever, or any ventilation with air from outside, so we increase fresh air coming into the room and reduce the CO2 concentration, for example. Yeah. Any local push button can also influence the situation, as already discussed. Here in this case, maybe to change the speed of the fan, or the presence detector, again to change the set point in case of presence or absence of persons. Here are solutions with so-called fan coil units. Fan coil units will be explained later on a bit more detailed. Components also with a heat exchanger, but also with a fan inside. Will be used both for heating and cooling. It can be used for both solutions. Yeah, a typical solution in commercial buildings like offices, for example. You see some additional icons representing electrical heater, as a further option to be controlled via a switch actuator output in the device, or a drip tray sensor detecting any condensed water linked to a binary input here. Can also influence the situation, means can also shut off air conditioning in case of condensed water in the system, or the window contact again. If you open the window, you also shut down the air conditioning solution. And of course again our room thermostat as part of the total solution. Example for an office room, the same we can do of course in a hotel room. A very typical situation, fan coil units, very often used in hotels, and the same situation based on the fan coil actuator. And some of you might know the same can be done with a room master. The room master is a multi-I/O device. The room master 1.1 and 2.1 has these fan coil outputs integrated to do the same as seen before with a fan coil actuator. Not only for hotel rooms, but very often used in such projects. Yeah, let's come to the sensors first of all. And I mentioned already we need a room temperature controller. You see here 5 different designs we have in our ABB range. The Bush Prion design, the Solo design. This one is not linked to any other design-oriented push buttons. It's a special fan coil controller made for this fan coil app operation or fan coil functionality, and you see a big display typically used in hotels, as already mentioned. Triton, and finally the RTC commercial, which is a room temperature controller as well, but you see no operating elements and no display to show any status or any room temperature. The others you can see have all displays, have all some local push buttons to operate something which has to do with temperature control, but maybe has to do also with other functions like the tree tone, for example. Also possible. So it's a component installed in the room to measure the temperature, to send out a control value, to compare the set point with a room temperature, and yeah, to send a telegram to the actuator. It can be a 1-bit telegram or an 8-bit telegram. I will come to this a bit later, and yeah, but this is necessary to have a, let me say, consistent solution, to have a closed loop regulation. Influences by the room temperature, by the set point, by changing it via the push button, of course, is also part of the solution, or changing the operating mode, for example, or the window contact, which also influences the solution. We have seen already in the former examples. Yeah, and additionally, already seen on former slides, the air quality sensor. It's a separate unit, wall-mounted, measuring the CO2 concentration, relative air humidity, and if you want, also the room temperature. But it does not control, like the other components, the room temperature, because there is no software to send out real, let me say, control values. So it's more for measurement, but the main application of this device is CO2 concentration measurement and sometimes also air humidity. So with this device you can control, of course, also a fan. Depending on CO2 concentration, you can program a threshold. You can increase the speed of a fan, for example. You could also open a valve if you want, and or a ventilation flap can be positioned in case of any, let me say, too high CO2 concentration. Additionally, you see here two LEDs, multicolor LEDs, to indicate CO2 and relative humidity. With 4 different colors, we can at least show the user in which range we are right now. So we can say, okay, if it's a red LED, it's a very high CO2 concentration, dangerous maybe. You have to take action immediately. If it's orange, it's not good, but not really dangerous, and further colors are available like yellow and green. So in 4 different levels, let me say, you can indicate optically what's the actual situation. The same for humidity. That's possible, so very user-friendly. But not only indication and measurement, but also actions can be done, as just mentioned before. And I mentioned already it's not only CO2 concentration, but also humidity and temperature. And this diagram shows you quite well the relation between humidity in the room and temperature, where you still feel comfortable. And you see the dark range here, dark colored range, between maybe 18 and 24 degrees is temperature okay, but the relative humidity should not have more than 70 degrees, or 70%, so between 40 and 70%. And with our solution we can influence this with a room temperature controller, but also with this air quality sensor. And with the right, of course, actuators and also hardware options to do this in a room. And again, finally, for the air quality sensor, you see here a diagram which components can be influenced by this device. The air quality sensor is heart of the system here, measuring the 3 different values, and you can control blower actuator, fan coil actuator. You can operate maybe also a shutter actuator if there's any motorized window behind for natural ventilation, also an option. So if you overshoot CO2 concentration, you just open a window electrically, either possible. And of course, any manual operation, any timer functions, any presence or occupancy dependent control can also influence the total solution. Back to our room temperature control. Room temperature controller as heart of the system, and here you see the main actuators we are using in our KNX solutions. We'll come to these electronic outputs later on, controlling valve drives directly, mainly for heating. You see here a combination of electrothermal valve drive with a valve drive actuator. We have an electronic actuator as well available, which also can also control motorized valves. We will come to this later. So typical solutions for heating. Here you see the direct KNX controlled motor valve drive. Here a combination of two devices. The universal interface, which can be programmed as an output, but it's not powerful enough to operate directly electrothermal valve drive, so we need a kind of amplifier in between, electronic relay, to do so. Not so often used, but also a solution we have. Yeah, and all, let me say, marked here icons representing fan coil actuators, controlling fan coil units. Main components here, the FCAS, two versions. The room master I already mentioned can be used as well, and the blower actuator as a further device. And Jürgen will talk about this later on a bit. The room controller is a device which can also control fan coil units or valves as well. Both possible. Yeah, electrothermal valve drives, very often used devices, and this component is also in our range, though it's not a KNX device. You see here all components which can control electrothermal valve drives. The control value is coming from the room thermostat, 1-bit or 8-bit. I will explain later on. So these are solutions for electrothermal valve drives. Okay. So how to control this? There are different options in the software of the room thermostat. One solution is a so-called two-step control. It's a software adjustment here in the room thermostat. Two-step control means that you adjust a set point, and additionally you program a tolerance, plus minus maybe half a degree or 1 degree from the set point. You're allowed to have the temperature in the room, and the target or the task of this device is to control the temperature within this limit. Means, let's assume the room temperature is going down. The room thermostat sends in 1-bit telegram and telegram to open the valve drive, so the valve will be opened. Solution you see here, valve drive actuator, for example, with the electrothermal valve. So 1-bit telegram will open the valve, it's heating up, temperature is going up again. If it reaches the upper limit, it will send a 0 telegram to close the valve drive. So then, of course, temperature is going down again, and the same again. This is a digital, let me say, situation on-off, but the valve drive itself, the electrothermal valve drive, is not reacting this fast. It takes 2-3 minutes to open completely, so if you start to open, it will slowly open, like this, for example. You see my pointer now, not completely open maybe during that time, and then you give an off telegram or a close telegram, and it will close again. Maybe not completely during this time, but then the next opening command will be set. So it's not a real positioning of the valve drive, but for temperature control, which is very slowly, it's very often a sufficient solution. So two-step control, one option. Or you program directly the pulse width modulation, which is a bit different. What does it mean? The room thermostat calculates a control value, as always, as a 8-bit telegram. It's a value, for example, 10% or 20%. But it will be converted into an on-off telegram as well. We call it pulse width modulation because during a certain period, a cycle time, we open the valve depending on the control value for this a certain time, and we close it. So example, 10% means 10% opening of the cycle time and 90% closing of the cycle time, which is in this case 15 minutes. If the new calculated value is in the next cycle 20%, it will open 20% of 15 minutes, 3 minutes. But again, electrothermal valve drive behind, it does not open that fast in seconds or milliseconds, it opens in 2-3 minutes. So maybe during 1.5 minutes, it will open only 50%, and then it will close again. But during 3 minutes, maybe it's completely open. So also a way of regulation and we only transmit on the bus here 1-bit telegrams on-off. Same principle, but a bit different in the way of calculation. Here is the following again: pulse width modulation programmed here in this room thermostat. We transmit the calculated 8-bit values, 20, 30, 50%, but it's only a digital solution here. It will be recalculated into pulse width modulation again. So we have the same situation as before. In a cycle time, we open more or less the valve drive depending on the calculated value. So on the bus is an 8-bit value, which can be used quite well for showing the actual position of the valve drive at the moment on a display, for example. And finally we have these motor valve drives. So either direct KNX, this is this one here, STK. So there's a real motor behind, which can open or close the valve behind directly. Or you use these non-KNX devices. It's not ABB product here, but it's a valve drive controlled via 2 contacts, opening and closing, like a shutter motor. And you see here the dedicated devices. The fan coil actuator, room master can do this, but also the electronic switch actuator. So direct continuous control, so-called, and you see it here in this diagram. We send also from the room thermostat 8-bit values on the bus. But from this solution, from this hardware solution, it will be directly, let me say, transferred to direct position. So if I send out 30% control value, within some seconds it goes to 30% opening or closing. So it's much faster. It's a more precise regulation, but it's more mechanic. It's cost a bit more, this solution. It's produced sometimes a bit noise, so not always necessary to use this solution, but a further option in our KNX world, let's say. And if you ask us, okay, which kind of solutions are used for which kind of heating or cooling applications, we have here some examples out of a documentation. If you have a radiator for heating, it's recommended to use pulse width modulation with a cycle time of 50 minutes, or also 2-point or 2-step control is possible, but mainly PWM, pulse width modulation, will be used. Same for underfloor or wall heating, very slow systems. There's a big mass behind to be heated up, so here very often pulse width modulation will be used as well, but with a longer cycle time, 20 to 30 minutes. Means the longer the cycle time is, the less telegrams you have on the bus, and if it's regarding regulation, okay, you can use this as well. Example for hot water fan heaters, so kind of a fan coil application, let's say. So we have a heat exchanger, but also a fan behind. So hot water based solution. A continuous control is here ideal, for example with the motorized valve drives, to have the air coming out of the system constantly, let's say. Electrical convector heaters, so with electrical circuit to be operated behind, also pulse width modulation with 15 minutes cycle time is okay. And last but not least, fan cooling, also fan coil units for cooling, also continuous control, and is recommended. Here an example for another parameter change for automatic transmission time. Transmission means if the control value calculated is different from the former one more than 5%, then the control value will be sent out and the valve drive behind will take some action. Summary of the different valve drives we can operate, which are on the market normally. Electrothermal valve drives, as already mentioned. We have some components, typically 2-step controller pulse width modulation. 24 volt or 230 volt valve drives are available. Then these electromotor valve drives. So this one is ABB product here, this electrothermal valve drive, but this one not. It's a motor valve drive, not KNX, where we need the dedicated component like the electronic actuator or the fan coil actuator to operate this. But continuous control, or you use directly the STK, direct KNX controlled motor valve drive. Additionally, on the market you find sometimes valve drives controlled via 0 to 10 volt. So you need an analog signal here in this case. Two examples of of 0 to 10 volt valve drives. One is controlled via thermoelectrical principle, one controlled via motor. We have here the fan coil actuator FCA S1221 to operate this, and in some cases you need such a component. In former times we had only the analog actuator, still possible to use, but it has not the dedicated software to do so. So this is a right device for this kind of valve drives you might have in a project. And these electrothermal valve drives, only one slide to understand the principle, how it works. A very simple device, cost efficient, very reliable, let's say. And the principle is the following: that we need nothing else but electrical circuit to control this. So we have to close the contact to heat up an elastic element inside the device, which will expand in such a case, and then it will press on this valve behind. If it's a normally closed valve, then it will be opened by pressing down this pin here. And if you open the contact behind, means you cool down the elastic element, it will shrink, and then it will open this pin again, and the water flow maybe will be closed. It's a very simple device. We need nothing else but electrical circuit behind, a contact behind, and the functions behind you have seen in the last slide is two-step control or pulse width modulation. Let's come to some actuators now. We need very often. I will show you something around the electronic switch actuator and valve drive actuator, very often used. You see here one device which has also manual operation part behind. You will find this kind of manual operation in some components. I will come to this a bit later. But here the typical situation. We have our room thermostat, KNX room thermostat, connected via KNX to our electronic actuator in such a case, in this case here, where we connect our valve drives. Either the electrothermal valve drive, or if you want, also the motorized valve drive. Possible with the electronic actuator. And for different applications we have discussed already, mainly heating, but in some special cases also cooling. Ceilings will be operated. Can be also fan coil units, though we have their dedicated device you will see later on. Available in two versions, with 4 outputs, 4 channels, and also with 8 channels. So 8 independent outputs. On which kind of outputs do we have? Electronic switch actuators, so-called. Electronic outputs, so no mechanical outputs, like switch actuators. The advantage here is that we have no noise. It's a wear-free, let me say, hardware. And over, let me say, the operating hours of such a solution, you have a lot of switching cycles. Think about the lifespan of such a solution. Many years it shall operate valve drives behind without any problems. And over this long period you will have a lot of switching cycles. So any mechanical relay might be damaged after a certain time. And that's the reason why we prefer, in this case, electronic outputs. You will find in this electronic switch actuator, but not only, other devices as well. So we can control electrothermal valve drives, motor valve drives, but additionally, if you want, you can use it also as a normal switching application to operate any lamp loads, for example. But be careful, only up to 1 ampere. So the nominal current of one electronic output is lower than a mechanical output normally. And but with a load up to 1 ampere nominal current, you can operate this as a normal switch actuator output. It's possible. So it's a special additional application here. And you see here the connection diagram as an example. Channel A connected to electrothermal valve drive. So one channel necessary only. Channel B, lamp load. The next channel. And channel C and D now in use for operating a motor valve drive. Keep in your mind, then you need two channels because we have two inputs in such a motor for opening and for closing. So two contacts are necessary. Operating voltage can be 24 to 30 volt AC/DC, you will see later on in the summary. Yeah, different from this, we have a further electronic output called valve drive actuator. Very similar, but there are some differences you should know. Again, the application not really different. Room temperature control together with the room thermostat and our valve drive actuator controlling thermoelectric valve drives, but no motorized valve drives. Not possible here. So that's one big difference. Only electrothermal valve drives can be connected here for temperature control. So one difference. Component itself has more channels than the electronic switch actuator. We have 6 outputs available or 12. So independent outputs. You see here already the rated current in the middle of the text, 160 milliampere per output. Remember, electronic actuator 1 ampere. So resulting in less valve drives which can be connected in parallel to one output. But also here I will explain a bit in the next slide. Yeah, also here's the same way of manual operation. Very simple. You find it in other devices as well. You press a button here in the middle for activating manual operation, and then you can operate each channel individually, can open and close the output to test your valve behind, for example. Again here a connection diagram. So no lamp load can be connected, no motorized valve drives, but electrothermal valves per channel. You see a connection, in total in this case 12. So it's a 12 volt switch actuator for valve drives, electrothermal valve drives, typically. Yeah, and to compare both solutions we have just discussed, the electronic switch actuator, ESS, but also the valve drive actuator. The main differences here in such a table quite easy to understand. So electrothermal valve drive for both. Valve drive actuator more channels per device. 3-point valve drives, lamp loads only for electronic actuator, switch actuator. And here a small difference. In some special cases you might need maybe a 24 volt DC valve drives behind, only connectable or operatable via the electronic switch actuator. So remember, the electrothermal valve drives, they need external power. So 24 volt or 230 volt is on the market typically. If you need DC you have to use the electronic switch actuator. But for AC, no problem, both can be used. And here's a current difference. You see, both the nominal current but also peak current is really different. 160 milliampere compared with 1 ampere. And what is interesting in such a situation, how many valve drives can be connected. Yeah, and you see here up to 4. Okay, with 230 volt you need lower current, less current, up to 4, but only 2 with 24 volt, but much more here for the electronic switch actuator. Okay, that's valid for our ABB electrothermal valve drives, because there we know the current. But in some cases people have to connect more than one valve drive to one channel to save channels. And you see, there's a big difference. That makes it maybe interesting to use also the electronic switch actuator. Yeah, and finally, costs per channel are a bit lower in the valve drive actuator. So regarding hardware, KNX hardware, it's a bit lower. But depending on your situation, you have to evaluate what is the most cost-efficient solution. Regarding software functionality, it's more or less the same in both devices. So there's not really a difference. Okay, so I would stop here and would like to hand over to Jürgen now. Jürgen will start or continue with the fan coil units and actuators behind, and will show you also a very interesting solution later on in reality and practice how it works together. Just a moment, please.
Hello and welcome to the second part of this webinar HVAC. My name is Jürgen Schilder and I'm continuing this webinar I would like to show you some details how to control fan coil units by using the fan coil actuator and the room thermostat. Like also to assign group addresses to the room thermostat and to the fan coil actuator, and additionally a small visualization program which shows you how this fan coil actuator and the room thermostat can work together. So let me start with a small overview about heating and cooling. Like we have here a typical office building or a hotel. Maybe in the cellar or in the basement we have our cold water generator, which creates or which produces the cold water into two pipes, one outgoing and one pipe here is coming back. And additionally we have here a central heater boiler, and this device here produces our warm water. So together or altogether we have here a so-called 4-pipe system, 2 pipes for cooling and 2 pipes here for heating. In all rooms we have the so-called fan coil units. A fan coil unit consists of the heat exchanger for the warm or cold air. Additionally, a fan with up to 3 speeds. To control these fan coil units, we need our so-called fan coil actuator FCA/S. The fan coil actuator can control the valve drive for heating and the valve drive for cooling. Additionally, this fan coil actuator can control the fan with up to the 3 speeds. The fan coil actuator is connected to KNX and communicates via our KNX room thermostat, for example here the 6138. And depending on the current temperature and the set point, the room thermostat sends the control value here to the fan coil actuator. Additionally, the room thermostat is listening to the magnetic read contact, and now when the customer or the hotel guest opens the window, then he sends the command control value 0, close here the valve drives and stop the fan. Or listening to a time switch or a keycard reader, then he changed the mode, the comfort mode to standby mode, and send different control values here to our fan coil actuator. So on the next slide you can see what is inside such a fan coil unit. At first we have here our 4 pipes, here 2 pipes for the cold water, the incoming and the outgoing, the same here for our warm water or hot water. Additionally here our valve drives for heating, the valve drive here for cooling, and all these valve drives and the fan now is controlled via our fan coil actuator FCAS. The fan coil actuator is also has also the possibility to control an additional electrical heater. Some of the fan coil units have this additional heater, for example, to heat up the room very fast. Now when we have there's a maximum difference between our current temperature and the set temperature, the room thermostat can control additionally this electrical heater to heat up the room very fast. The fan coil actuator can listen additionally here to the window contact and change the mode to a kind of anti-freeze mode, and here for example another input which is listening or which is connected to a drip ray sensor or a sensor which monitors the filter, for example, and depending on this input the fan coil actuator is controlled in different modes. So here's an overview about the heating and cooling principle. Here on the bottom you can see the temperature, maybe from degrees, 5-10 degrees up to our set point here for heating, which is 20 or 21 degrees. So here we start our heating set point, then we have a kind of dead zone, a distance between our so-called heating set point and the cooling set point. So this is in real practice about 2 or 3 kelvins. And then we have here our set point for cooling, which is for example 24 degrees, and then we are in the so-called 2 cooling mode. So we have here 25, 30 and more degrees in our room. So depending the temperature, the room thermostat is here in the so-called heating mode when we have less than 21 degrees, and more than 24 degrees, for example, we are in the so-called cooling mode. The room thermostat can send 2 different control values. One control value, for example, for the cooling, and then the fan coil actuator is opening the valve for cooling and goes here in the fan speed. The thresholds of these different fan speeds, 1, 2 or 3, is now a parameter of the fan coil actuator. So the room thermostat sends only the control value, for example 65%, the fan coil actuator receives 65% and goes automatically into fan speed number 2 and opens the valve for cooling. And the same principle again, it becomes cooler inside the room, 24 degrees, less than 24 degrees. Both control values, heating and cooling, are 0, less than 21 degrees in our room. And then we start the heating mode and the room thermostat sends the control value heating 50, 60 and more percent. So the first device I'd like to introduce you is a new device, a so-called blower actuator FCLS X611. X mean it can be a 1 or 2, so we can control with this blower actuator with the device FCLS 1611 single phase fan, so with up to 3 speeds. So here we have the connection to our fan up to 3 speeds, the incoming phase, and additionally we have a switch output here. This switch output can be used independently, our fan, for example, to switch on, as for example, the light in a room, or maybe some of the fans need a kind of central command to switch on. So we can also control here a central command to the fan input. So the next device is the FCLS2 611. The 2 means here we can control 2 independent fans. Here the fan number 1 and here the absolutely independent fan number 2. Additionally, we have 2 switching outputs like before to switch the light, for example, or to switch on a main switch in our fan. It is also possible to use these 2 switch outputs, for example, to control valve drives, but only in an easy way. We can open or close the valve drives, but we have no parameters like we needed for pulse width modulation. So basically it is possible to control valves, but only in an easy way. And here's the overview how to use such a blower actuator in a room, like for example here in a meeting room. We have here kind of ventilation system. So inside the room we have our room thermostat 6138 to do the heating control inside the room. Additionally, our air quality sensor, and which measures the CO2 concentration, the humidity, and send the value to KNX bus. Additionally, the device sends the different thresholds, and via these thresholds we can control here our blower actuator and change the speed of the fan speed number 1, 2 or 3, for example. Now when we have to when the CO2 concentration here is rising, and then the blower actuator goes in a different fan speed 1, 2 or 3 to blow out the CO2 concentration out of the room and to get fresh air inside. Here our second output, the relay output, we can use it for switching the light or other things, and for easy function here we can also control valve drives. So this works in our so-called automatic control mode. So the air quality sensor sends the control value and the blower actuator is listening to this control value. So another possibility is to change the mode instead of this automatic mode to use the so-called direct mode. So we can use, for example, here one rocker, and by pressing one rocker, left side of the rocker, we can change manually. So the end user can change here manually the speed of the fan. So we can assign here one group address and press on the left side of the rocker, and then the sensor sends a command to the blower actuator, stop the automatic mode and go direct to the fan speed number 1, for example. Another possibility is to use the right side of this rocker to parameterize this, go to fan speed number 2, the next rocker, left side, fan speed number 3, and here on the right side, for example, fan off. This is one possibility. Every time we press here on the second rocker on the left side, the fan goes into the fan speed number 3. Or we use the so-called up-down mode. So every time we press on the left side, the sensor sends a command, fan speed up, and on the right side, fan speed down. Down from fan speed number 3 to 2 to 1 and off. So we have different possibilities to control the fan manually, or by sending one byte. So for example, when we send here 1 byte with the value 2, the blower actuator goes in the fan speed number 2. It's also possible. And maybe via one other rocker we can send the information, go back to the automatic mode and listen again here to the air quality sensor, or via time function. Maybe after 60 minutes Someone started here the direct mode, it jumps back to the automatic mode, and then the blower actuator is listening here again to the air quality sensor. So here about the connection schematic of our blower actuator. The actuator with one output, we have here our incoming phase, for example the phase L1, and the three outputs for the speed number 1, second speed, and the speed number 3. And with the second output here, our relay, we can here our incoming use another phase, phase L2 for example, and switch a load, like here our light circuit, or additionally for example a valve drive with on-off functionality. The 2-volt blower actuator, we can control two independent fans. Here the fan number 1 with the incoming phase L1. Here for example the switch output. Here again our second fan with the phase L3, and the second output use another phase. So here we can control two independent fans and two independent switch actuator outputs. Good, so far the blower actuator. And now I continue with the fan Coil-Actuator FCA 11M. M means here manual operation. You can see we have here our standard manual operation principle. By pressing long this button here, the fan Coil-Actuator goes inside the manual operation mode, and by pressing this button we can test our fan coil unit and change the speed of the fan, or open here for example the valve for heating, the valve for cooling, or we can simulate here the binary inputs. So this so-called fan coil actuator is a device to control standard fan coil units. We have here on board two electronic outputs. One output to control our valve drives for heating, and another output to control the valve drives for cooling. It is possible to connect thermoelectric valves or also 3-point valve drives like motor valve drives, like Thorsten explained it before. Additionally, we have here the output to control the fan with up to 3 speeds, and a switch output for switching the light for example, or some fan coil units have an additional electrical heater inside, and with this relay we can switch on this electrical heater maybe in the winter time to heat up very fast the room. So on the bottom here we have two binary inputs. These binary inputs are independent the fan coil actuator. What does it mean? For example, we can connect here our magnetic read contact on the window and send the information window open or closed via KNX to our room thermostats, and then the room thermostat send back the control value to the fan coil actuator, maybe open or close the valve drive and stop the fan. The second output can be used for a drip tray sensor, or maybe for monitoring the filter of the fan coil unit or something else. So to use this manual operation we need here KNX. So it's necessary to connect this fan coil actuator to our KNX power supply, or we have a kind of commissioning adapter which is also available for testing here the manual operation. So here's our connection diagram. The first output here, this switching output, it's recommended to use this for the additional or auxiliary electrical heater in the fan coil unit. Then our fan with up to 3 speeds, and here the output for the valve for heating, the valve for cooling, electromotoric valve drives like here, or standard thermoelectric valve drives 24 or 300 or up to 230 volt. And on the left side here our two binary inputs. So the ETS application, we have a lot of parameters. The first step is really to read the manual or the technical data sheet of the motor. We have to change some parameters which depends on the behavior of the motor. One important parameter is which kind or which type of fan or the motor works, for example. Is it a motor which works like the changeover switch or the step switch? This is very important, and I explain these parameters here on the next slide. Or is it necessary to have a kind of startup behavior? For example, when we want to have fan speed number 1, is it necessary at first to go to fan speed number 3, stay for example 10 seconds in the fan speed number 3, and then the fan goes back to the speed number 1 to get for example more energy, or to come on turning for example. So is it really necessary to have such a behavior? Yes, and then we can set a parameter. Or is it necessary that we need a minimum time in a level? So for example, when we are on speed number 1, we want speed number 2, number 3. Is it necessary that the motor or the fan blows maybe a fixed time, 10 seconds, 20 seconds in one level, and then it's possible to go to the next level. Additional parameters here, for example, for the thresholds, the fan Coil-Actuator receives the control value, maybe 50%, and then we can specify 50%, this is my fan speed number 2, 80% fan speed number 3. Additionally, we have some more features inside our fan Coil-Actuator. One is the so-called limitations. The fan Coil-Actuator, we can have up to 4 limitations. Limitations are working together in the automatic mode and controls the fan speed, our range of the fan speed. For example, during the night, it is possible to limit the speed of the fan. So we can send a command to the communication object, limitation. Now it's a kind of sleeping mode during the night, and the maximum fan speed can be now 0, so the fan can be off, fan speed number 1 or fan speed number 2. And it's not possible that when we have activated such a limitation, that the motor goes in the fan speed number 3, because during the night it is maybe to reduce the noises of the motor. Or another limitation is, for example, when the room is not occupied. So via the keycard reader, for example, or presence detector, it is possible to send a command to the fan Coil-Actuator, activate limitation number 2, room is not occupied, and then the fan every time works in the fan speed number 1. The fan does not stop or goes in fan speed 2 or 3 every time the motor is in the fan speed number 2 or the fan is fan speed number 2 when the room is not occupied. For this example, you can use the limitations. Additionally, we get a lot of status messages back from the fan Coil-Actuator sent to KNX. For example, the position of the valve drives or the stage of the fan. So maybe on the room thermostat you can really see the speed of the fan, or on your visualization or something else. And we can monitor the control value, which is sent by the room thermostat, maybe cyclically every 5 minutes. And it's a parameter what should happen if the fan Coil-Actuator does not receive this control value. We can set a parameter what should happen with the fan speed, and the position of the valve drives, and a lot of more things. So for the direct mode, we have several communication objects. For example, here is the one bit object for up and down. So via one touch sensor, for example, push button with one rocker left side or right side, we can change manually the speed of the fan. Or for example, we can make with rockers go to fan speed number 1 or dial 2 to a direct fan speed. Or in the automatic mode, then he's listening to the control value of the room thermostat and goes in the different positions. So here's one of the very important parameter. How does the motor works of our fan? For example, do we have a motor which works like a changeover switch? Then we have to set it in the ETS parameter. So then the behavior of our output works a little bit different. Now when you see we have the fan speed number 1, then only our output here is closed and all other outputs are not closed. Next fan speed number 2, the first output opens the relay. So then we have a short waiting time, and then the next output close. So every time only one output, the relay is closed. And in the fan speed number 3, both outputs, the first outputs are open and only the last output is closed, and the motor works in the speed number 3. Or do we have a motor which works like this principle via a step switch? Then you can see the different. Fan speed number 1, only the first output is closed. Fan speed number 2, the first and the second. Or fan speed number 3, the first, the second and the third output is closed. So this is very important to read the manual, the technical data sheet of the motor, which principle the motor works, and use the correct settings inside the ETS parameters. So the next fan actuator we launched is the fan Coil-Actuator FCA 1221. Here we have in principle the same hardware device. The only difference is we have here 3 binary inputs, one more. And instead of our electronic outputs to control our electrothermal or motoric valve drives, we have analog outputs between 0 and 10 volt. So here it is possible to connect valve drives which needs analog signal, and then this valve drives in the position. So here we have on the left side the output number 1 to control valve drives for heating, and here the valve drive for cooling. So the other outputs are still the same, the fan with up to 3 speeds and our relay to switch on electrical heater or something else, for example. So here about the wiring diagram, you can see on the left side which is different. Here we have our analog output signal between 0 and 10 volt to control our valve drive, and here the valve drive for heating, and everything else, the motor or the fan with up to 3 speeds, electrical heater and so on, is still the same. Good. So now I would like to show you a small example about room temperature control with a fan coil unit in a hotel room. Like here we have a standard hotel room with our room thermostat, our fan coil actuator FCA 11M with the electronic outputs for the valve for cooling, valve for heating, a fan with up to 3 speeds, and connected to the binary input a magnetic reed contact. So I don't show here the KNX sensor for switching the light or controlling the shutter, only here the solution for heating and cooling controlling. So how to link the communication objects? At first let me start with the standard with the automatic mode. Automatic mode means that the room thermostat measures the temperature, and depending the current temperature and the set temperature, he sends the control value heating to the fan coil actuator, to this communication object control input heating, or in the cooling mode then we need another group address to send the control value cooling. So we need minimum here 2 group addresses, one from the room thermostat with the control value heating and one control value here for the control value cooling. Plus the so-called status of the fan speed, because we want to see on our room thermostat the speed of the fan. Now when we use, for example, here the 6138, we can see here the status of our fan speed. This is really the group address which comes back from the fan coil actuator and change here the icons, and now we can see fan speed number 1, 2 or 3. That's why we need here additional group address, and then we see the correct status of our fan speed. These are the minimum group addresses we need here for linking between our room thermostat and the fan coil actuator in the so-called automatic mode. Additionally, it should be possible to change manually the speed of the fan, the so-called direct mode. Maybe by pressing the button on the room thermostat 6138, we can change manually the speed of the fan. So we have to link this object here, fan stage manual, via a 1 byte group address here with this signal or with this communication object fan speed switch. So and then we can press here the first time, we send the command fan speed number 1, press again fan speed number 2, and so on. So additionally we need another group address which gives our fan coil actuator the information should he listen to the manual or the direct mode or to the automatic mode. That's why we have to link here one group address, fan automatic manual, and link it here with this object. And then when we press our button on our room thermostat, then the bit here changed and the fan collector knows that he has to listen here to this manual or to the direct mode. Plus again, the status back from the fan coil actuator, is he in the manual mode or in the automatic mode. So we need additional for the manual or direct operation, again 3 group addresses. So in the next situation, we want to listen also to the to the magnetic reed contact, which is installed in our window. This magnetic reed contact is connected to the binary input in our fan coil actuator to the input A. So we need another group address. Link here this input A from our binary input and link it to the communication object frost heat protection. So this binary input works independent. Our fan coil actuator, he sent only the status, the logical 1, window open, and then the room thermostat, when he receives here the group address with the 1, knows okay, the window is open, and then he sends the control value 0 for heating, 0 for cooling, and the fan coil actuator closes the valves and stops with the fan speed. So another possibility is to use the so-called limitations. One limitation, we can simulate, for example, here with our input B or via a time switch, for example. So we assign one group address to the limitation 1, the so-called sleeping mode during the night, and then we activate here with the logical 1 our limitation, and then the motor, for example, of the fan is limited to the fan speed 0, 1 or 2. So the control value here, for example, can send 100%, open the valve, but during a fan limitation is activated, the fan goes only into the limited maybe speeds, for example maximum speed number 2. So we need again here one group address to disable or enable our limitation. Another limitation, for example, is a so-called absence, so nobody is in the room. We can use here, for example, a keycard reader or by pressing one rocker. So now one group address is linked here with the object limitation number 2, and in the parameters of limitation 2 we set here the range of our fan is every time speed number 1, and the group address is linked also to the communication object forced operation heating and cooling. Now when we remove our keycard, the logical 1 goes to this forced operation object, the valve for cooling now is closing, the valve for heating is closing, and the fan limitation 2 is active, and every time the fan blows in the speed number 1. So, plus we have some more status information from our room thermostat, maybe the current set point for cooling, for heating, or the current temperature, which can be displayed on a comfort touch or something else for the information. But these here are the minimum group addresses we need to link between our room thermostat and our fan coil-actuator. So now I have prepared a small exercise here on my KNX training panels. Some of you are KNX training centers and you have these training panels made by Desto. One is, for example, here our room thermostat 6138, and this room thermostat we can change manually here the speed of the fan. Here we can change the set point for heating or for cooling up and down, and under here this room thermostat we have a kind of rotary knob, and behind this rotary knob there's a potentiometer, and this potentiometer we can simulate the current temperature. So when you turn left, we can reduce our current temperature, and turn it right, we can increase our current temperature. And then we can simulate here different situations, heating mode or cooling mode. So here on the right side I have the KNX demo board of our fan coil-actuator, simulates here up to 3 speeds of our fan, the valve for heating, for cooling, and here our 2 binary inputs. The first one is the magnetic read contact in the window, and the second one I can simulate, for example, here our limitation, our sleeping mode, what happens during the night. And I have created a small visualization project based on the ISPA visualization, and after the webinar you get a feedback email including the ETS project of this example here and the visualization project also. So now I share my desktop and show you this visualization. Just wait some seconds. Okay, now here this is the so-called ISPA visualization. In the mode, everything now is running at the moment. Here on the left part I have the communication objects and of my room thermostat 6138. On the right side my fan coil-actuator with some status messages, for example the valve for heating, the forced operation for cooling, or for the valve position. At the moment you can see this is really red, so now the valve for heating is now open, for cooling it is closed. The status of my 2 binary inputs, and in the middle I can see here, for example, my group addresses which I need for linking between the sensor, my room thermostat, and the actuator. So here I have the information about the current set point of my room thermostat. At the moment 23 degrees for cooling, 20 degrees for heating, and here the current temperature. At the moment we have nearly 18 degrees inside the room. So 18 degrees, the current temperature 18 degrees, the set point for heating 20. So the room thermostat is in the heating mode and send the control value, for example here about 96%, nearly 100%, to the fan coil-actuator. The fan coil-actuator opens the valve for heating and goes in the fan speed number 3. So now at the moment we are in the direct mode. The fan Coil-Actuator is listening here to our room thermostat. And via the potentiometer, for example, I can change the current temperature inside the room. Yeah, and after some seconds you can see the current temperature or actual temperature now changes here, and the room thermostat calculates again a new control value and send it to the fan Coil-Actuator. So we have to wait some seconds because the room thermostat calculates every 10 seconds a new control value. Just give me some seconds. And now you can see the current temperature I simulated are nearly 20 degrees. So he calculated a new control value for heating, for example 49%, send it to the fan Coil-Actuator, and the fan Coil-Actuator, the valve for heating is still open, but he goes in the fan speed number 2. Now when we go inside, for example, the cooling mode, so I simulate here a current temperature more than 23 degrees, and then you will see that the room thermostat is going from the heating mode to the cooling mode. So the control value should be here 0, and he sent the control value cooling more than 0. Please wait a little bit. Just wait. So, okay, now I simulated a current temperature with nearly 30 degrees. Now what happens? You will see he calculated a control value for heating 0, but the control value for cooling is up to 100%. The fan Coil-Actuator closes the valve for heating, but he opens the valve for cooling, and goes here on the fan speed number 3. Because we have here 7 kelvins difference between a current temperature and our set point, and then there is the maximum cooling mode. So now I can simulate that a hotel guest opens the window by using the binary input number 1, number A. So now I open here the window. Oops, nothing happens. Sorry. Yes, okay, now you see here now my window is open. He sent the group address to the room thermostat. The room thermostat goes to the frost heat protection. The new set point for cooling is 99 degrees, for heating 7 degrees, and he sent the control value 0 for cooling, control value 0 for heating to the fan Coil-Actuator. The fan stops, the speed you see here 0, and the valve for cooling and the valve for heating is now closed. So I close my window again, and the room thermostat goes back, sends the control value 100%. The fan starts in the speed number 2, this was the startup behavior, and after some seconds in the speed number 3, and the valve for cooling now opens again. So for the manual or direct operation, I can really simulate here when I press on this button number 1, then the fan Coil-Actuator goes in the so-called manual or direct mode. He's no longer listening to the control value, and I can change manually, for example here, the speed of the fan. After a fixed time or by pressing here my automatic button, then he goes back in the automatic mode and he's still listening to the control value of the room thermostat. So during the night, for example, I can start a kind of limitation. Limitation 1, this is for example so-called sleeping mode. The hotel guest is inside the hotel room. We have a control value 100%. Open the valve for cooling, fan speed number 3, but it is during the night very noisy. So we can activate here our limitation. I do it via a switch sensor, for example. And limitation means we limited the speed of the fan, an ETS parameter. I said the limitation of the fan is here off, speed number 1 or speed number 2. Then you can see the motor goes only in the speed number 2 or 1 or off. It's not possible that the motor goes in the fan speed number 3 because it's too noisy. Then I disable the night mode, and then he goes back in the fan speed number 3. Or now when I leave my hotel room, I remove my keycard reader, I simulate it by another sensor, so the room is not occupied. Then I activate the limitation 2. The information goes to the fan Coil-Actuator, the valve for heating now is closed, the valve for cooling, and the limitation 2 is active, so the speed of the fan is every time speed number 1. Independent our control value, which then 100%, 0% or 50%, limitation 2. I have limited the speed of my fan every time speed number 1. So far, a small example how a room thermostat can work together with a fan coil actuator, the parameters, the behavior, and you get this presentation, you get the visualization project, the ETS, so you can also play here with the system a little bit and see the behavior after the webinar. Good, so far. Let's go back to my presentation. About documentation, HVAC, there is one, I think, a little bit old brochure available as a PDF file, heating, air conditioning and ventilation. We see it is here with EAB. It shows, okay, this is some years old, but the information is still valid inside. You can see some little bit older KNX devices or EAB devices, but it is a good description about HVAC heating and cooling, how to install a room thermostat and how the different the pulse width modulation works and so on. So the topic inside is still up to date, but only some little bit older KNX devices. Additionally, we have our application manual, heating, ventilation, air conditioning, which is available also on our internet. And we have online also our e-learning modules, and especially we can recommend one e-learning module, a so-called room climate control. You can start this e-learning module. You have not to subscribe or something, or also your customers can do it, and you get about a nice presentation. It's available in German and English language about room climate, fan coil actuator, heating and cooling. Good, some more information about our next trainings here in Heidelberg. So we have in Heidelberg our next KNX Advanced course. This is a certified KNX Advanced course which takes place from Monday the 30th up to 4th of July. KNX Advanced course follows the KNX rules, so we have here topics like heating, cooling, ventilation like before, security, constant light control, DALI, or how to control also media via audio, video and so on. But this advanced course is necessary before to attend a basic training. So maybe if you are interested for your customers, we have still some places free. It is a training about 5 days, but you must before attended a basic training. After the advanced training, you can stay 2 days longer, and then we have our KNX application training, 2 days, also about our KNX desktop devices. And for some of you who wants to become a KNX tutor, we have our KNX tutor course in the middle of October. Then you are allowed to give also KNX basic and advanced training when you become here a tutor. But to become a tutor, you need really deep experience in KNX, a long time, and before you have to attend the advanced training and of course the basic training. Our next webinar will take place on Wednesday, 9th of July. So remember the date. It's about shutter control. Shutter, blinds, lamella, Venetian blinds, everything about our shutter actuator JARA/S. So you get also invitation letter before, of course, but still remember here the date, the 9th of July. Okay, so far, thank you very much for attending this webinar. We wish you a nice day. Hope to see you or again the next webinar. Goodbye.
Okay, gentlemen, bye bye, ciao.